Hi, my name is Rizky Putris and my student number is U7033006, as you can see here. Okay, I want to discuss about decision theory. Decision theory is one of basic in the machine learning. So the idea of decision theory is that it is kind of approach in decision making in the uncertainty environment. So I want to discuss about the introduction first, about how to quantify the uncertainty. And next one is the recap probability theory, and the next one is about decision theory itself. Discuss about the general criteria in making decision. It contains three approaches. The first one is minimizing the misclassification rate. Next one is minimizing the expected loss, and the last one is the reject option. After that, I want to discuss about inference and decision, which is in this decision theory, it will be breakdown into two. That is inference and decision. Discuss about how to approach this kind of method. And the last one is loss function in the regression. So the first one is I want to give you a brief explanation about what is decision theory. This one is making optimal decision in situations which is involving the uncertainty environment, as thus it will be used in the pattern recognition. So how to quantify the uncertainty? The first one, we have an example of the uncertainty about the polar ice when it will be melting. The idea is that we can know how quickly we think this polar ice is melting by using a lot of diagnostic information, for example in the satellite image, and then we can revise our thinking about this ice loss. So we can quantify this uncertainty in our expression by using Bayesian interpolation of probability. So next one, I want to discuss about the probability theory. So we have what we call a joint probability, which is the number of occurrence given I and j divided by the total of the events, and then we have marginal probability, that is the probability of, for example, here we have x equal to xi. It is equal to the sum of occurrence probability of I and j, but it's given the sum of in the j index. And the next one is we compute the conditional probability, that is y equal to yj is given by x into is equal to xi. So it's equal to the number of occurrence between I and j divided by ci, that is similar with I mentioned above. So the next one, we have sum rule. So we have px is equal to the sum of pxy given I, and then we calculate this is one for the discrete and this one is for the continuous. And we have what we call product rule. Product rule is equal to pxy is equal to py given x times px, or it's similar with px given y times py. So by substituting these two equations, we can get this what we call Bayesian rule or Bayes theorems. Here we have what we call posterior. It means that we have px given y is equal to the likelihood, which means that py given x times the prior, that's px, divided by the evidence. So next, about decision theory, we need to have the input vector that correspond to the vector t, which is what we call a target variables. So our goal is to make a prediction of t given a new value of x. To get this decision, we need to determine the what we call a joint probability distribution. So we call it pxt. And in regression, the target variables is continuous variables, while in classification, it's represented as class levels, which is a discrete. So we have this next example here. So we have the X-ray of pneumonia patient. So we have the vector X represented as the set of pixel intensities in the image, and we have the output, that is the absence of pneumonia or presence of pneumonia, which is represented as C1 for absence or equal to 0, and C2 for the presence of pneumonia, with T equal to 1. So we need to determine the joint distribution of pxck from the training data, or we similar with pxt. It will give the probabilistic situation, a description of the situation. So our goal in this kind of problem is that given an X-ray of image, that is X, so what is the class of this image? So it can be represented as the posterior probability pckx is equal to this formula, as we have mentioned in the Bayesian theorem. So the next one that I want to discuss is about general criteria in making decisions. So we have three approaches here. The first one is minimizing misclassification rate, and the second one is minimizing the expected loss, and the last one is the reject option. So the first idea is minimizing misclassification rate. So it means that if our aim is to minimize the chance of assigning x into the wrong class, which means that intuitively we would choose the class having the higher posterior probability. So first of all, we need a rule. The first one is assigning x into available classes, and then divide into input space into regions called RK. So we can call it decision regions. And the next one is we need to define a boundaries which divide these regions, what we call a decision boundaries. So in our previous cases, in polynomial cases, we have two classes. So we only have two regions here. So in order to get the probability of getting a mistakes, is that we need to calculate the probability of in area in R1 given the C2 plus Px given in the R2 but in the C1. So we from the sum rule we can get this formula. From this formula we can draw a graph of both Px_C1 and Px_C2, so we can see here. And then we have a decision boundary called x hat here that is divided into R1 and R2. So as we can see here, we have a blue region which is belong to Px_C1 but in the region 2, and the green one is in the Px_C2 as well as Px_C1 but in the R1. And we have the red region here that is belongs to Px_C2 but in the R1. As you can see here, if we drag the decision boundary into x0, the red region will be vanished. So it means that if we move this into region, which means that the misclassification rate is low. So the idea behind this is that if we can get the minimum misclassification rate in decision rule, so that we need to assign the x which has the highest posterior probability. For example, if we here is x have the higher in the C1, so we set just in this region into R1. While as you can see here, if the Px_C2 is higher in this region, so just set from this into this one, this belongs to the R2. So actually sometimes our objective is not just simply minimizing the number of misclassification. So let's go back to our previous example, that is pneumonia. So for example, we have a patient that does not have pneumonia but diagnosed as having it. So the patient will suffer the treatment that's probably redundant, and the patient will be spent a lot of money to this redundant treatment. And the other cases is that if the patient has pneumonia but diagnosed as not having it, I think this case is more problematic than previous cases, because the patient will have a lack of treatment. Possibly in the future it will be fatal. So in this approach we have proposed what we call a loss function, or we usually call it a cost function. So this kind of measurement that calculates its loss for any available action, and we compute it into every classes. So our goal is just to minimize this loss function. So we have what we call a loss matrix here. We denote as LKG, which means that we assign new value of x that have true class CK, then we assign this x into CJ. Sometimes CJ is equal to CX, but it's not always. Sometimes it could be different. So for example, here we have from our pneumonia cases, we have true class having healthy, diagnosed as healthy is 0, having healthy but diagnosed as pneumonia is 1000, pneumonia healthy is 1, having pneumonia but diagnosed pneumonia is 0. So this is one of the example of it's not good enough. The next one is, as I mentioned before, we need to minimize this loss function. Sometimes this loss function depends on the true class. However, this is still unknown. So in here, given the input factor x, that is our uncertainty in the true class, is expressed into the joint probability distribution of PCK. And then we need to get the minimize of average loss or expected loss by this following formula. So in some application, it will be appropriate if we avoid making decisions in ambiguous scenario, in anticipation of a lower error rate on this example for which a classification decision is made. This approach, what we call a rejection option. It means that we reject for the probability if it's kind of ambiguous and let the human do the decision. So the idea is that we have a threshold called theta here. So if the probability is lower than theta, we just reject the decision and let the human do the decision. So the next one is I want to discuss about the inference and decision. So this classification problem is broken down into two separate stages. That is the inference stage and the decision stage. So the inference stage, which it means that we use the training data to learn the model for the posterior probabilities, and then the decision stage, then we use these posterior probabilities to make the class assignment. So another alternative approach is that we combine these stages by simply learning the function that maps input to x. So we call this process is discriminant function. So in inference and decision, there are three approaches. The first one is determining the class conditional densities, the Px given Ck, for each class individually, and then we also compute the prior probability of classes, and then we need to find the posterior class probabilities, that is PCK given X. So this approach, we can call it a generative models. And the second approach is that we use discriminative models, that is determining the posterior probability PCK given X. And then we use decision theory to assign a new X to one of the class. And the last one is that we have what we call discriminative function, which maps its input X directly onto the class label. So the merits of these approaches is that the first approaches, that's approach A, is very demanding because we need to compute the joint distribution over X and PCK. So we know that we need to compute the probability of XCK as well as the prior probability of PCK. So it will be problematic if the training data is very large. And in order to mitigate this kind of problem, so we use the approach B, is that instead of calculating the joint distribution, we only need to compute the posterior probabilities. And the next one, the approach C, so there's a simpler method, that is we just find fx that maps X into the class label. So here in the approach C, we no longer use P posterior probability. However, there is a reason that maybe approach A is better compared with the approach B and C. So here we have two graphs. So the first one is the class conditional densities, like here, and that has having input variable X here. So, and the right one is we have a posterior probability given the input X, like this one. So we can see here from the blue graph, that is this one, it shows that this plot has no effect of the posterior probability. And these class conditional densities may contain a lot of structure that has little effect on the posterior probabilities. And the next one is we have a green line here. So in the posterior probabilities, we need to define this decision boundary. While if we're using the class decision, we have no longer to use that. So the next approach is that it's given a simple method, just mapping X into the class label T. So this approach is not using the posterior probability. However, there are strong evidence that we still need this posterior probability. So the first one is just consider a problem in which the elements of the loss matrix are subjected into revision from time to time. So such as, for example, it will be happen in the functional application. So if we know the posterior probabilities, so we can trivially revise the minimum risk decision criterion by modifying this formula. If we have only the discriminative function, then any change in the loss metric would require that we return to training data and solve classification problem afresh. And the next one is the posterior probability will allow us to using the reject option. So if we don't have this posterior probability, we cannot know how to make this reject option. As you know that this reject option can minimize the misclassification rate, so it will be better if we use the posterior probabilities. So the next idea why we need to use posterior probability is that sometimes the problem is very complex, so that we need to break down into the sub-problems. Let's get back into the pneumonia. Instead of using the X-ray, why don't we also use the blood test data, for example? So by using our posterior probabilities, we can get the probability of X-ray and X blood given the class of pneumonia or not. Because in the blood test and X-ray are independent, so we can get this formula. In order to get whether the patient have pneumonia or not, given the blood test and the X-ray image, we can compute into this formula, and we substituting this one into this one, and we can get into this formula. Previously, we are mainly talking about classification, but now we need to know how to compute the loss function in the regressions. In classification, we set T is equal to in discrete variables, or we set into a different classes. But in the regressions, we set the T is equal to continuous value, which is estimating Yx for each input of X. We can get the expected or average loss is become here. Usually, we use the loss function that is a square loss, which is equal to Yx minus the square. So we just replace our loss function into this. So we can get the expectation loss into this formula. The next goal is that we need to choose Yx that minimize the expectation loss. So we can get this Yx by applying the revision of expectation loss with respect to the Yx, so that we can get this formula which is equal to 0 because we want to minimize the expectation loss. And then by applying the rules of probability, we can get that yx is equal to the mean of conditional distribution pt given x. So this is known as the rejection function. There are three distinct approaches to do the solving for regressions. So the first one is determining the joint distribution and then normalize to get the posterior probability. And lastly, we marginalize to find the conditional mean of yx given by this formula. So the next approach is that we need to find the posterior probability and then subsequently do marginalization to the conditional mean similar to this formula. And the last approach is that we just map the regression function directly from the training data. So to sum up, decision theory is one of approach that is making optimal decision in situation involving the uncertainty. So in decision theory, we need input vectors x which is correspond to the vector t that we call target variables. So our goal here is to predict t given by a new value of x. In regression, we set t into a continuous variables, while in classification, we set t into the discrete variables, or we just set into the class. General idea to get the optimum result is that we have three approaches. The first one is minimizing the misclassification rate. Next approaches is the minimizing the expected loss. And the last one is the reject option. And next one, we have three approaches in making the inference and decision. The first one is computing the joint distribution by calculating the cross conditional densities here, and also the classifier for each class of ck individually. And then we compute the posterior class probabilities. And the second one is we need to determine the posterior probabilities, and then we will use the decision theory we have discussed before. And the last approach is that we need to create a function which map x into the class label. Similarly to the classifications, the regression have the same approach of these three approaches, but it uses t in the continuous form and find yx for the decisions. So that's all for my presentation.